I've recently been asked several times what I think of quantum computing. I am a technical, nerdy person with a layman's, maybe even a hobbyist interest in physics, and I'm a programmer. So my immediate answer is that I find it fascinating. It gives us a new insight into physics, which is great, but it also allows us to solve some kinds of problems that are, for all practical purposes, insoluble without it. Quantum computing is very different to traditional computing. It isn't like the difference between object orientation and functional programming, or even punched cards and solid-state disks. This is a very, very different kind of thing. In some senses, it may not even be computing in the way that we usually think of it. So what is quantum computing, and how and when are you likely to be writing code for quantum computers? Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't been here before, please do hit subscribe. And if you enjoy the content here today, hit like as well. Thanks first to our sponsors, Equal Experts, Octopus, Tricentis and Transfic. They all support our channel, so please do support them in turn by checking out their links in the description below. I am not a quantum computer programmer. But like you, I'm living through the time of their birth. So I approach this topic as a programmer and a layman interested in quantum computing, but by no means an expert. I have the slight advantage that my brother-in-law worked for a company that works on emerging quantum technologies. So he has sanity checked some of my approximations. Thank you, Bernard. I have an approximate understanding of quantum mechanics and its application in quantum computing. So if you want the real answers, I'm afraid you're going to have to do quite a lot of work. I think it's fair to say that we're still very much in the time of pioneers and are not yet ready for settlers as far as quantum computing goes. Quantum computers hold the promise of making some things possible and that until now have not been possible. This opens new opportunities for solving whole new classes of problems. One of the groups of people that are most excited at the prospect of quantum computers are physicists. In fact, the idea of quantum computing was invented by physicists Richard Feynman and Yuri Manin in the 1980s. The person credited with the practical invention is usually Oxford Professor of Physics David Deutsch. Their interest is primarily in improving our ability to model reality, from the subatomic particles where quantum effects define what really happens. The quantum calculations in particle physics explode horribly. It's so horribly, in fact, that it's hard to make predictions beyond tiny numbers of particles using conventional computing techniques. A functioning quantum computer gives us a tool that can be used to more directly model these sorts of systems on bigger scales and will almost certainly add new insights. But it can do a lot more than that. Quantum computers are weird, and the most significant way in which they're weird is how the efficiency of calculation scales. We're used to thinking about the costs of our algorithm at some level, how long it's going to take for us to get a result. A quantum algorithm doesn't slow down in the same way as you add more parts. In fact, you don't really add more parts. There's one part, a matrix, and you just add new entries to the matrix, and the quantum algorithm processes that matrix in a single step, however big it is. One of the common examples of this is cracking codes. Most encryption is based on factoring large numbers into primes. One way to solve this is by trying every possible combination and see whether that gives you the right result. This is obviously a dumb idea for a digital computer. In fact, cryptographers pick numbers that are so big that you can't crack them by brute force this way. Trying every combination would take more than the age of the universe. But what about a quantum computer? It can solve these kinds of problems in much shorter time frames, ridiculously shorter time frames. Because of this, most people assume that quantum computers will make most current cryptography techniques obsolete quite soon. So there are people busy working on quantum safe encryption techniques all over the world, some of them using quantum computers to do the encryption. There are applications for quantum computers in AI too. AI often involves processing very large quantities of data. Quantum computers can potentially speed that up quite dramatically. In chemical and biological engineering, quantum computers can help to more accurately model, simulate and manipulate the engineering of molecules, from the quantum states of their subatomic particles upwards, which means dramatically more realistic simulations. We currently struggle to calculate quantum effects at molecular scale because the calculations explode so fast. But a functioning quantum computer should be able to allow us to do this. Quantum computers have already demonstrated successful simulations of simple chemical reactions in this way. This suggests that we'll be able to model molecules we'd like to design, simulate their behavior accurately in a quantum computer, and then, when we get the right one, manufacture them. That could revolutionize medicine, but maybe even material science and engineering too. There are all sorts of potential applications: financial modelling, modelling complex manufacturing processes, and weather forecasting, to just name a few. So how do these machines work, and what does programming them look like? I'm going to use the Everettian many worlds interpretation of quantum physics to try and explain some of these ideas that quantum computing is based on. I'm not qualified to judge whether this is right, but it seems the easiest way to visualize it to me without the maths. When talking about something this new and innovative, we'll need to set the foundations, and like every other explanation of quantum computing that I've found so far, we'll need to explain what a qubit is. This is a foundational idea, and to do this, I'm afraid I'm going to have to explain something else that I'm not really qualified to explain, some of the properties of quantum physics, so do bear with me. And bear in mind that my explanations here are only very rough approximations to the truth. Quantum physics is the deepest, most profound explanation of reality that we have. It describes with unfeasible levels of precision how very small things like atoms, electrons, photons and subatomic particles work. It's stood up to every single experimental test so far for over 100 years. This is how stuff works as far as we understand anything. This is more true than anything else that human beings have discovered so far, by many orders of magnitude when it comes to the precision of experimental results. Yet, at the same time, it tells us that reality is disturbingly crazy. When we try to interpret the results of quantum physics and think about what they mean in the real world, we get crazy answers. For example, arguably the simplest explanation for what quantum physics is telling us is that we live in a quantum multiverse, and each time a quantum event happens, a new timeline of events is selected or maybe even created, a kind of clone of the universe, including everything in it, including us. This may sound like the ravings of a crazy person, but in many ways, if you ignore the extravagance of there being a possibly infinitely uncountable number of versions of the universe and of you for a moment, the many worlds or Everettian interpretation of quantum mechanics requires the fewest add-ons and assumptions. Some of the other explanations get even weirder. In this interpretation of quantum physics, we are quantum beings. And the way that I interpret this means that we've evolved to inhabit the quantum universe. So there are times when we perceive a collection of timelines in the universe. And so the answers that we understand are somewhat fuzzy because we're looking at a broad set of possibilities, representing a range of possible timelines. And there are times when we narrow our focus and in effect more precisely narrow the selection of timelines that this version of us is inhabiting. You could think of that as selecting the position in the multiverse from which we view our results. I know this sounds crazy, That's because it is so far beyond normal human experience. But as far as we can tell so far, it isn't wrong. And it's directly related to quantum computing. Let's take a bit of a step back and talk about qubits. For this, we need to understand some of the key ideas in quantum physics. Let's start with the double slit experiment. If you have two slits and a screen and you shine coherent light through the slits, you get a weird effect. You get a series of bars on the screen. These are the results of interference, a classic property of how waves behave. Imagine the light as a series of waves that spreads out from the light source, and when the waves hit the slits, they're split and effectively create two new light sources. Because these are waves, as they propagate from the slits toward the screen, they will interfere with each other. In places where the peak of the two waves coincide, the sum of these peaks will be high. Where the peak from one wave meets the trough from another, they'll cancel each other out, and so you get these bars, these fringes, these areas of brightness that represent the intensity of the light on the screen. That's the result of the waves combining and interacting. This happens with light, so for a while everyone assumed that light was a wave. Except it's much weirder than that. Light isn't a wave. It's transmitted as particles called photons. And there is more physics that I'm going to skip over here that says photons are definitely particles. We can manipulate light down to the level of individual photons, little unitary packets of light. So you can carry out the same experiment using the double slits, reducing the intensity of the light all the way down until you're firing one photon at a time at your double slits. In a classical world, we'd expect the bars on the screen at this point to disappear. The particle would go through either one slit or the other. After all, there's only one particle. But that isn't what happens. You still get the bars. This means that a single photon is interfering with itself. A single photon is in two places at once. It gets even weirder than this, but this is an example of what is called superposition. The photon is in a superposition. At this point, we're looking at two different paths in the multiverse. In one path, the photon went through the left slit. In another, it went through the right. The wave effect, the bars on the screen, are showing us the probability of which version of the universe we're in. Wait, it gets weirder. If we put a detector at one of the slits to see which slit the photon went through in reality, the bars on the screen disappear. Because now we have, in effect, selected a single universe from which to view our results. A single timeline. So there's no longer any room for doubt about the path that this photon took. This isn't just true of photons. This is true of electrons and actually all matter. Everything works like this at this scale. So light and everything else is neither a wave nor a particle, or both. Particles are probability distributions. And the probability is the probability of being on a particular timeline in the multiverse. The interpretation of the double slit experiment is that the photon follows all possible paths, but that each path has a probability associated with it. In the double slit, it's 50-50, left or right. But we can have other superpositions with different probabilities associated with them. And this is how quantum computing works, by assigning probabilities and tracking them as they change. The next idea that you need to understand if you want to understand how a quantum computer algorithm works is the idea of entanglement, or spooky action at a distance, as Einstein famously called it. Quantum particles can be entangled with others, meaning that the state of one affects the state of another, even if they're on opposite sides of the universe. One way to think of this is that at some point, by measuring the state of one particle, we select which version of the universe we're in, and that automatically selects the state of the other particle. Imagine a pair of quantum gloves. One's left-handed and one is right. We put each glove in a box. You have one box and I have another. Maybe we selected who gets which box based on some quantum measurement. Now you get into a spaceship and travel to the other end of the solar system, or even the other end of the universe. At this point, the gloves are in a kind of superposition. They're both left and right. But if I open my packet and find a left glove, I immediately know that you've got the right-handed glove. Meanwhile, in the other timeline, in another universe, I found the right glove and you've got the left. What entanglement means is that we can build more complex structures of quantum states that are related to one another and interact. In fact, that is what the quantum multiverse is. So what's all this got to do with quantum computing? Well, fundamentally, this is how a quantum algorithm, works. A qubit is capable of holding a superposition of states, in this case binary states. It has the value of 0 and 1, rather than the 0 or 1 of a bit in a classical computer. And part of the programming a quantum computer is to assign the probability that this qubit will be either 0 or 1 when measured. Naturally, this gets more complex. While single bits and single qubits are interesting, you usually need more than one to do anything useful. So we need to assemble bits or qubits into more meaningful, more useful structures. In digital computers, these are often bytes, streams of bytes, or whatever whatever meaning we choose to assign to them. In quantum computers, the nomenclature that I've seen is that we assemble our qubits into circuits. These circuits are made up of multiple qubits with probabilities assigned to them and entangled in ways that we define. This combination helps us to compute some desirable result. Now let's be clear, in a true quantum computer, what I've described is not an analogy. We are establishing real quantum states and using real quantum entanglement to represent the relationships between them. Certainly, we can simulate this kind of thing in a classical digital computer and get useful results, albeit slowly. But one of the problems with quantum physics is that the number of calculations explodes. And so carrying out this vast, more than astronomical number of calculations in any sane time frame is impossible for a classical computer, realistically. Quantum computers are very, very different. Once we've set up the qubits, they're assigned probabilities to them and entangled them appropriately, any answer that we get takes the same amount of time. There is effectively no processing time involved. We just select which version of our universe our answer is in by picking our inputs, and there is the answer. We can get answers to questions that would take a conventional computer more than the age of the universe to calculate. All quantum algorithms can be represented as a matrix multiplication, but what the quantum computer does that is unique is to calculate that matrix in the same amount of time, however big it gets. Current quantum computers take between 50 and 250 nanoseconds to provide an answer, however many qubits are represented in the matrix. There are lots of challenges here. The physics is well understood, but not at all intuitive. The engineering is extremely difficult. Setting up and maintaining quantum states reliably and repeatably is incredibly hard. Current generations of quantum computers will sometimes give garbage results because of something called decoherence, where entanglement or superposition is lost. In this case, at the wrong time, before the results have been successfully calculated. You could think of this as selecting the wrong universe for our answer. Of crucial relevance to us is that programming these things is incredibly complicated. Setting up the circuit that represents our problem bears no obvious relationship to conventional programming thinking as far as I can tell. Nearly all of the examples of programming quantum computers that I've seen so far spend most of their time describing the digital programming tools that allow us to talk to and submit circuits to a quantum computer. They don't spend quite so much time talking about how to translate a problem into a quantum algorithm, a circuit. Despite all of this, people have written quantum algorithms. One of them, for example, can do a quantum Fourier transform, which is a way of analysing a signal for all of its component parts. I think that maybe you can see why this sort of problem is a good fit if you watch the computer file episode that I've put a link to in the description below. It describes superposition in quantum computers. My guess is that quantum programming is never going to be mainstream. It's always going to be difficult and very mathematical. Mapping problems into useful circuits to solve real problems is certainly starting to happen. But I think that this will probably always be a somewhat esoteric endeavour. I think it will remain the realm of deep specialists. I'm probably completely wrong, but I don't anticipate that the day when the average Java or Python programmer will be writing quantum algorithms alongside their tests and writing YAML scripts. There's no real quantum equivalent of Hello World, although inevitably people have implemented one. These things don't interact with the world that way. There are tools that we will use to solve otherwise insoluble problems, but we will organise them, feed them with inputs, orchestrate their use and render their outputs with conventional digital computers. At the current state of the art, it takes pretty smart people to program these things. I think that as time progresses, we'll learn more and that will become a little bit easier. But if I'm honest, I doubt that it will ever be easy. And I doubt that you'll be able to do it without understanding the maths of quantum physics. I'd like to finish on an even nerdier point than the rest of this episode so far. One of David Deutsch's interests in quantum computing was to use it to prove something that he believes the many worlds interpretation, the Everettian interpretation of quantum physics. One of the early quantum algorithms was invented by Peter Shor. It was designed to calculate prime factors in the way that I described earlier, which is why cryptographers are so very nervous. In quantum computing, even a relatively modest number of qubits can outperform all of the computers on the planet for the right kind of calculation. Shor's algorithm is possibly proof of the reality of the many worlds multiverse that I've used here to explain some of the quantum physics concepts. This is pretty mind-blowing. Here's a quote from the book, Quantum Computation and Quantum Information. When Shor's algorithm has factorized a number using 10 to the 500 or so times the computational resources than can be seen to be present, where was the number factorized? There are only about 10 to the 80 atoms in the entire visible universe, an utterly minuscule number compared with 10 to the 500. So if the visible universe were the extent of physical reality would not even remotely contain the resources required to factorize such a large number. Who did factorize it then? How and where was the computation performed? Mind blown? Thank you very much for watching.